Professor Hulin Wu. He has actually a primary appointment in the Department of Biostatistics at the School of Public Health, and he has a secondary appointment in our school. He came to us last September from the University of Rochester School of Medicine and Dentistry, where he was professor and founding director of the Center for Integrative Bioinformatics and Experimental Mathematics.
Wow. Okay, thank you. So because I'm new here, in this school and also in the School of Public Health over there, I'm trying to give a talk to introduce my research so that we can, build more collaborations or to know each other more, in details. And actually, my background is I got my bachelor degree and a master's degree in engineering school from, basically in the major of electrical engineering. Then I've got my PhD from the statistics, that's in the School of Art and Science. Then I worked, my first job actually in Memphis, Tennessee, not far from here. That's in the math department in the School of Art and Science. Then I work in the medical school, now in the School of Public Health, now then also School of Biomedical. I travel many different kind of schools, to work. And so the experience is quite, different. And today I gave a talk called Precision Medicine in the Big Data Era from a rocket science perspective. Because right now all the talk in the medical school or in the medical center is precision medicine, so I have to follow this trend. So everybody, gave a talk about this. And so probably all of you know that, the big data and the precision medicine is very closely related, because of Obama's three initiatives. In the 3 years ago, he had an initiative called Big Data Initiative, and that year they invested $200 million, for the big data. And then in the year of 2013, and there's another Brain initiative. They invest a lot of money to generate a lot of data from Brain. And then last year, this Precision Medicine initiative, and that's another $200 million, for this purpose. And so all these initiatives, actually, my understanding is all of this involve like big data management, analysis, integration, and also involve like data-driven or computerized decision making. When you try to, invest a lot of money to collect data from, it doesn't matter from brain or from, the healthy human subjects, and the question how to integrate this data, how to analyze data so that you can use this information for decision making. This is not easy, actually, task. And then when we try to talk about the evolution of medicine, that's many, many years ago, when people treat, patients, basically that's based on, experience. It's so-called empirical medicine. So like in particular, like Chinese traditional medicine, basically based on the personal experience and based on very limited personal experience. It's hard to quantify, so people, why you give this thing a little bit or that a little bit, even they don't tell you what a little bit means. And so in the Western medicine, it's more like right now use so-called evidence-based medicine. That's based on the randomized clinical trials, right? Right now, FDA control this very tightly. All the drugs you have to go through all the rigorous clinical trials to prove, the new drug really works, based on the evidence. Evidence means the data, actually. And then, probably about 10 or 15 years ago, when the sequence technology is more popular, then there's a new term called personalized genomic medicine. I put the genomics there because at that time, 10 or 15 years ago, when people talk about personalized medicine, that's basically based on the genomics data, sequence data to adjust people's treatment. That's at that time. Now we talk about the precision medicine. My understanding is this precision medicine is different from this personalized medicine based on the genomic data. Now this thing is based on, basically this is called data-driven personalized medicine based on the big data from a big cohort. That's the plan, I think, right now. That's the evolution, how this medicine goes, thing. And as you know that for the precision medicine, last year in September, this is the report for the design of the precision medicine from the NIH. So the basic idea is try to recruit 1 million or more subjects. And this year, I think our school is trying to apply for this, at least one of this project. totally, this year, NIH put like at least I think $500 million for this, for people to compete. That's a big investment, and so basically, when NIH invest money, try to recruit this 1 million or more subjects. What they will do is they request people to collect data from these 1 million people. Those data include basic demographics and also self-reported data that includes symptoms, quality of life, smoking or not, or alcohol use, whatever. A lot of self-report data, and also behavioral lifestyle data that include diet, physical activities, and also sensor-based wearable device data that include location, activity monitors, whatever, all those kind of data. And also definitely for clinical phenotype data that's from the hospital, and also from imaging technologies, the EEG, maybe other hospital machines or technologies over there. And another type of data is omics or molecular and lab data. There's different kind of omics data there, and also different kind of lab data, and also environmental data that includes GPS, air quality, weather, whatever, those kind of data, and also the other data that includes social network, Twitter, whatever, the social media, So it looks like include everything, whatever data you can collect from each of these 1 million people, they will collect it. So, I'm not sure how realistic is this. So, but this is very challenging. The question is, after you collect this data, question is how and who will do data analysis and integration? It's unknown. In that report, they only tell you, go to collect data, recruit subjects, and right now, what we are trying to compete for this grant is only, they call the recruitment center, or try to recruit subjects, and also coordinating center means you have to, once you recruit subject, you collect data, you put data in the center. But never mention who and how to use the data, to analyze data. So that's, that so far there's nothing there, So, and so what that means is right now the precision medicine project data analysis is not planned, and it probably will be separated from data collection and data management. So right now they are trying to build a data management center and recruitment center, maybe some other technology centers, but not data analysis center. And this is good or bad. You separate the data analysis from data collection and data management. And the good, the process. So probably in the future they will make the data publicly available. Anybody can access or analyze data. So which is good, right? Make everybody make the data available to everybody, to all the independent investigators. And the cause is, problem is, because the data analysis is not considered in the study design stage, and the data may not be efficient. When you collect the data, maybe some data are useless, and some data, you're supposed to collect, you didn't. So that's quite, possible. So this is some pros and cons when you consider these things. And also people I know came here for interview. Jiajie asked a question, how precise the precision medicine can do. Okay, so when you talk about the precision medicine, the word precise, where it's coming from? I think this precise, word coming from the rocket. There's so-called, the precision guided or whatever rocket. So that's the question is, when we look at the rocket, how it works, then we can probably get an idea whether this precision medicine is really precise. So that, I'm not sure I can make this video works. So this is the video for kind of rocket, and maybe turn the light a little bit lower. So you can see the rocket is like 50 kilometers away, and so you can hit a truck or car very exactly. This is really precision guided missile. Okay, and so this is a very short range. You can see how accurate it is. And even right now, the technology, the rocket type technology, is so good that even several thousand miles away, they still can hit a truck, the rocket, so accurate. So that's the precise. What do you mean precise? The precision. My question is, can we do this, in medicine? So when we think about this, why the rocket is so precise? So when you try to understand why is that, Because for a rocket, you can write down all the equations. I just give you a so-called ideal rocket equation. Just based on the Newton law, you can write down the different equations to describe how the rocket flies. And then you can use a control system to control the rocket to hit the target exactly. So the key point is you can write down the exact differential equation or mathematical representation for the rocket, and all the parameters in the differential equation almost very, very accurate. For example, for the gravity, constant like d0, we know that parameter is 9.8, in the middle school physics, right? And that parameter is so accurate, not that accurate. It's not exactly 9.8. Actually, it's supposed to be 9.864, whatever. There are many digits after that. We don't learn that in details, but when you do the rocket design, you do need to consider many decimals after 9.8, okay? Even depends on which direction you shoot the rocket, you still need to adjust this constant, in different ways. The trajectory are different. You have to adjust this so-called the gravity constant. You have to adjust a little bit because, the Earth is not round, right? You know what? Do you know what shape it is? Flat. Okay, good. Any idea what the shape of the Earth is? What's that? Like an egg. Any others?
It's like an onion.
Like onion. Okay. It's not round. It's not ellipse. Actually, it's like a pear. And even it's not regular. The Earth is not regular. That's why these parameters have to be adjusted depending on which direction you go. What's the gravity over there. You have to adjust that to make the rocket so accurate. Okay. So, but even that, so these things can be very accurate, even which direction you shoot, this direction, that direction. They can get this, derive this. There are many thousands of papers you can find to adjust this, probably 9.8, 5 decimals after that number. Try to get that exact so that you can shoot the rocket more accurate. Okay, so that's all the parameters, equations you can use the Newton law to exactly derive. That's how the rocket is accurate. Can we do this for human body? Can we do this for medicine? That's the key. If you cannot do that, I don't think you can do that rocket. If you compare a human body or any animal or any living being to a rocket system, this is kind of like two complex systems. Both of them are very complex, multi-levels. For the rocket, there's a first stage, second stage, third stage. Here is the fourth stage, or they call the load. Basically, if the rocket tries to shoot a missile, you put a bomb here. Or if you try to launch a satellite, you put a satellite there. Okay, that's called a load. Okay, that's the different stages. For a human being here, this is a cell. Our body consists of cells. Inside of cell there are proteins, RNA, DNA, whatever. A lot of things inside each of the cells. Then there are many types of cells. Many types of cells consist. That's our organ. Consist of the many types of cells. Different organs have different types of cells. Now we have many organs. Then we become a system. And that's a human system or animal, whatever you do, depends on the medical research what they are doing. Okay. So that's if you look at this also levels. The DNA, RNA, protein in the cell control the cell behavior, and different type of cells interaction. Maybe build your immune system, your liver system, whatever the system is, the organ, and then the organ system build your whole system. And same thing for the rocket. But however, if you compare these two systems, which one is more complex? Both are more complex, I know. Which one is more complex? Right. This any the human system, right? Usually people say, oh, this is not a rocket science. It looks like rocket science is the most complex system. Actually, it's not. This one is much more complicated than this because you know that even within one single cell, there's how many genes? 20. For human, probably 20,000, more than 20,000 genes. For the mice, there's 30,000 genes. There's so many DNA, RNA, proteins, whatever. If you count the numbers in one cell, there are a lot. And how many cells you can count? How many cells in your body? How many organs? But for the rocket, roughly in a rocket, the inside of this rocket, roughly probably 3 million to 6 million elements. Okay, depends on how big the rocket, the purpose of the rocket. Roughly 3 million to 6 million elements inside. Okay, this much smaller than this. This is probably billions of. If you consider RNA, DNA, trillions or whatever, DNA, RNA as one element, so it depends on how small that. So that this one is much more simpler than that, this is much more complex. And and also we can make this one is very accurate because you really can use mathematics to exactly describe the behavior, not only each of the elements, but also the whole system. So that's how when you look at the rocket, when you try to learn, rocket is so precise, want to do this for medicine precise, why rocket system is, precise, so as I mentioned, right now we understand the physics and engineering principles and laws for each of the elements and also for the whole system. Okay, so that's no problem. So, and also for the system mechanism, very well quantified. As I mentioned, we can exactly write down the equations. Otherwise, the rocket is not precise. Okay, and all the parameters are known. Not even if not known, we can measure it very, very accurately, even after 6 decimals, whatever. So that's the thing. And also, we can design, control, manufacture a rocket system. There's no problem right now. It's very easy. It's not that complicated. It's very easy to do this. But for a biological system, right now we are just trying to understand some of the biological principles and each of the elements, which means try to understand. I know some of those wet labs, in their whole life they only study 5 genes. Just 5 genes. There are so many. Or another lab only look at 3 proteins in the whole life. So that's what people try to understand. Each of the lab try to understand a piece of the elements, and so that we can understand some of the biological principles, and from a system level, and so only qualitatively we understand some of the pieces, not the whole system. So that's the thing. And also we try to intervene or modify the system, like by giving drugs or whatever, you do some therapy to modify something. But we definitely cannot manufacture, we cannot design, we cannot, I don't know how to design a human or something. This is hard. So compare this, this is a very premature, right? This is quite premature. So that that's the. So my understanding is the precision medicine will not work if we just collect a lot of data from 1 million, even more subjects. We just put all those omics data, molecular data, whatever, phenotype, clinical data, behavior, whatever environment together. You just put data together, doesn't make anything. Right now they give maybe more than 100, 10 million or more than that probably, 70 million for the data coordinating center, right? They basically put data together. And so that will not work. If you just put data together, data cannot speak. We always say, let data speak. Data itself cannot speak. You have to know that. And second thing, if we just analyze all the different kind of data separately one by one, then put the result together, still doesn't work. Okay, you never integrate them together. You just, let's do omics data. I'm an expert on the, omics data analysis. I just do omics. I'm an expert on the clinical. I just do clinical. That doesn't work. You just do this separately. And also, machine learning or data mining techniques are not for precision medicine. This is for data exploration, but not for precision medicine. Okay, prediction, because all these technologies, prediction with errors is not precise. So if you want to be precise, you have to, like a rocket, you have to exactly describe the system in a quantitative way, with accurate quantitative way. So that's the thing, so that's the thing. So that's why, precision medicine, why it works. Precision medicine will work if we understand the human body system and its interaction with the environment at all levels in a very quantitative and systematic way, which is very difficult and very expensive if you want to do it. That's why precision medicine try to invest a lot of money, but even that money is not enough, far away from enough. And also try to understand the disease pathogenesis very clearly, and also understand treatment or drug mechanism very well in a quantitative way. Okay, I just understand in a quantitative way. Just qualitatively, roughly is not accurate. Again, precision medicine you want, precise. And so this is the question: Can we quantify a biological, complex, multi-level biological system? So this is like from the DNA, RNA, protein. I know many of us working on, the genomics data, genetics data, protein data, proteomic data. This is just one single cell. Just doing this, and cellular level, and the organ level, and the whole system. Can we build a model to describe this? So this is the challenge. The challenge is so far in physics, in rocket science, there's a lot of Newton laws, the law of dynamics, law of air dynamics, flow dynamics, whatever. You can use a lot of mathematical laws there. But in biology, there's no Newton laws so far. And we are not sure what mathematical representation can be used to describe the behavior of biological systems. Different equations really work. I will talk about different equations, but I'm not sure that works. Just try it. And also, the relationship in a biological system is very complex. It's nonlinear. Right now, all the experimental people think the relationship is linear and binary way. Okay, this mutation, make this gene high expressed and make those genes low expressed. Oh, this is a negative correlation. So let's just think about the binary simple correlation way. But actually, all this relationship of genes, protein, cells, all these factors are nonlinear. Okay, and also the biological system is living, is a dynamic system instead of static. So if you just look at one time point thing, snapshot, that may not be the whole mechanism for the system. Okay, and also as I mentioned, it's a multi-scale complex system. It's genetic, protein, cell, organ population, and really need integration instead of reduction approach. Right now, more and more people talk about the integration or so-called system biology approach. And but when people talk about system biology approach, they think, oh, if I measure the whole genome, okay, I'm doing system biology because I didn't miss any gene. I try to measure all the genes. That's not the whole system. Genes, that's only one level. You have to do all the levels. So that's really, system biology, like a rocket system. So again, so what kind of mathematical models are available for us to use to describe a biological system? I just listed some of these models. Like right now, very popular, mathematics is like different equations, different equations. Alternate different equation is very, simplest one. Then you can have delay or hybrid or partial different equations, stochastic. You can use all of these different equations because different equations try to model some kind of dynamics change, right? That's why it's, because the biological system is dynamic, it's living. So that's why usually people use a lot of different equation models. And I will talk about the first one, simplest one, and even the simplest one is difficult. And then maybe differential equation or state space model. This is usually used in the control theory or rocket science always use these things. And stochastic process models, branching process, agent-based models, network models. There are many, many, many more. So the question again, we don't know which one is is good to exactly or precisely describe a biological system. We have to try. You try all of them, and maybe you can get one. So that's the thing. Right now, our strategy we call 3M modeling strategy. So number one, first M is multi-scale, which I mentioned that gene, protein, cell, organ, all the levels we have to put together. Second M is I call it multi-model types. I will focus on different equations, but we also try different type of models to see which one is. We compare them, which one is better to describe the system. And also another M is we call it multiple data sources because only one lab's data or even one school's data is not good enough. We have to try to use all the public data and also knowledge from literature. There's millions of papers talk about the genes, protein, cells for different diseases. So those are very useful data also. And also the question of how to integrate our own data with this public data and the literature knowledge. So this is the question. We have our own data. We do our own experiments also. So this is the thing, when we try to do the modeling. So in the past 15-something years, as a PI, co-PI, probably I received a lot of different kind of grants, probably total more than $30 million. I received another $30 million probably as a co-investigator, but it's not my own grant. So it looks like a lot of money, but compared to a rocket science, when you design a rocket, much more than $30 million. I mean, the biological system is much more complicated, than the rocket science, but the money is very much smaller than the rocket science. Can you do it? That's the thing. So, but in the past 15 years, in particular, I got a center grant called Center for Biodefense Immune Modeling, and this one, basically, I will focus on this one. In the past 10 years, we have done a lot of work on this. The purpose for this center grant is we try to use system biology approach to establish a computational mathematical system to quantify immune response to flu infection and also to vaccination. So at different levels, gene, protein, cellular levels. And then we try to use multidisciplinary techniques to do this. The purpose actually NIH gave us this grant 10 years ago is after 9/11, they are afraid of the bioterrorists. if Biostatistics modify the flu virus and release it, make it more lethal, and the question is how to shorten the preparation. Usually when you identify a virus there, you have to identify what's the difference this new virus with the existing one, how to quickly develop drugs and vaccines to respond to it. Usually that process takes 10 years or maybe 15 years, but that's too late, right? Then the NIH said, can you use mathematical model computational approach to basically build models first, and then there's new virus, they can quickly do some experiment, then you can use the model to do simulation to identify what's new for the new virus and how to quickly identify the target for drug and vaccine. So that's the purpose. Then that's why we get this money, and this is like $22 million grant for 10 years. And so basically, we have, I'm the PI. My co-PI is the as a kidney transplant immunologist. He's MD, and so we do have these labs. We do have like these 8 labs actually to do experiments, to collect data. And we do have mathematical modeling core and statistical core to deal with data, bioinformatics core to manage the data and put data together. And also we have education core, try to educate scientists how to use computational tool to do the research. So that's the basically this project we designed this study for both to collect data from both human and mice and simultaneously and parallelly. And for the mice, what we gave is we inject the flu virus to mice, then we kill the mice, then we harvest the lung, spleen, lymph node, blood, whatever organs. Then we cut those organs to many pieces. Then we send different pieces to different labs to measure whatever they can measure in the immunology. Because we focus on the immune system, so we ask those immunology virology labs to measure whatever you think are related to the immune response to flu infection. Measure it, CD4, CD8, antibody, whatever. See, that's the thing. But for the human, we cannot directly give the virus. Actually, we can. At the University of Rochester, we reserve a floor of a hospital, actually, isolate that things that's supposed to be used to challenge people with virus, real virus. We did that many years ago. Usually the college students like to participate in that because they put the college student there for 2 weeks. They give them probably $1,000 or $2,000, and you cannot go there when we have to stay in the room. You can play computer games or make phone calls, but you cannot walk out of the room. And they will give you the food, whatever. The nurse will measure your temperature every day. Some of them will develop symptoms, some of them will not, but they will receive several $1,000s and to stay there for 2 weeks and to do these flu challenge studies. But right now, what's that? No, you cannot control that. So that's a problem. For this, we can measure the response, immune response for all the organs. But this, only thing we can get is blood. And sometimes our nose swab. Nose swab can measure the virus, virus load, flu virus load. So that's what we did this. But this one we cannot do the flu virus. We use the flu vaccine. If flu vaccine is a modified virus, we use the seasonal vaccine to mimic the virus. Then we collect the blood and to measure different kind of immune cells and immune responses. That's a limitation. Okay, so basically when we try to build models based on this data, we have to look at. You probably cannot see it in the back. So I think this panel. Let me see. So so A to C. This panel is the data from our own center. This data is from the public databases. And so this one is gene level, protein level, cellular level. This is gene level, protein level, cellular level for public, and this is for our center. And this is time point. How many? Because when we do the different equations or try to model this dynamic system, we have to measure the things in time, right? And depends on how many time points. This is 1 to 3, 4 to 6, 7 to 9, 10 or more time points. So you can see our center, measure more data in the longer time or more frequent time points in gene, protein, cellular levels. In the public, people measure only 1 to 3, usually only 1 to 3 time points. That's why most people ignore the dynamics. They just try to just 1 or 2 or 3 time points. So that's doesn't matter if it's gene level, protein level, or cellular level. Okay. So this is the number of data sets. These are 50 or something. This is all for flu data sets. How many flu that we can get from public and from our center. And then we try to use all this data to build our different equation modeling. So that's the thing.
What is the
So that depends on the virus. Like a flu virus, our virus will go to the peak at day 3 or day 2 or day 3, right? So you have to have a lot of frequent measurement time point in the first 3 days, several hours, and after 3 days, the virus go down, and then up to day 7 or day 10, the virus go to 0, and then that's the range. Then you just usually we do daily, but for the early time we do half day or something. So that's the thing. And you can see this is the time course. This is day 0, 1. Usually we do the daily up to 12 days, and we do another 21 days, 35 days. So this is a different. Basically what we get is a curve. We measure the curve. This is like a inflammation, and this is like a viral load curve. This is like the antibody presenting cells. This is like CD4 cells. When we measure different kind of things like gene expression level, cellular level, or protein level, everything is a curve. That's because only 10 or 11, 12 days, the virus, you can see the virus almost 0. This black one is the virus load. So that's what we measured. A lot of data. The question: can we use a model, mathematical model, to describe the interaction of all these different kind of components at gene level, protein level, cellular level? I didn't show you all, but here is the data from. I think this is our data from RNA-seq at gene level, gene expression level. So this is like this X is the genes, like 20-something thousand genes. These are time points, like up to 12 days, and this is the gene expression levels. This is for 6 subjects. This is human data. For 6 subjects, you can see the different people have different response. They give the same vaccine, flu vaccine, but the response pattern, are completely different. This is a heat map, So that's why you have to personalize. If you don't personalize, different people are really, really different. So this is the thing, and then we develop, a pipeline to model this time course gene expression data using differential equation models to link them, link these dynamic interactions between different genes. Now there are many steps. I don't have time to talk about details. Like first step, we identify temporarily differentially expressed genes. Now not all the 22,000 genes, differentially expressed after you give the flu vaccine. We identified roughly several thousand of them, 2,000 or 3,000 usually. And then we cluster those significant genes into groups because many of those genes actually the response pattern is very similar. So you cannot distinguish them. So you have to group them. Then we use differential equation models to link those, we call super genes or group of genes, and into a network. And then we refine the parameter estimate. Finally, we do annotation, then put them into a network format. This is just gene level. This is just one level at like rocket first stage, okay, gene level. So this is the thing. Basically, differential equation means that. So this is the one gene change. Differential equation left-hand side is the derivative. That's a change of one gene's expression. It's maybe related to all other genes. We don't know which gene it is. Then we have to use the data to identify which gene is related to this gene. So if maybe only 2 or 3 out of 20,000 genes related to that particular gene. Now we do this one gene by one gene. Okay, let's go through all the genes. That means that this differential equation is very, very high. Even we only identify several thousand of significant genes. If we write one equation for each gene, that differential equation dimension is 1,000. Okay, 1,000 means this parameter you need to estimate is 1 million. You have to estimate 1 million parameters. Even this is linear. I just put this linear, very simple, simplest differential equation model. Try to describe just one level, gene level interactions. It's 1 million parameters. None of the parameter Not like a rocket. They know that the parameter exactly after 6 decimals even. But this one is hard. So that's why we have to use a statistical approach to do this. This is like the group of genes. You can see for this from the lung. This is the mice data. I think this mice data we can get this gene expression level from the lung, and we cluster those gene expression into about 32 groups. Within each group, these genes are similar. These gray lines are the many genes, different number of genes there. But within each group, they are similar. But for different groups, you can see they are different. So that's why we have to cluster them, and then we build a differential equation network between these clusters or between these groups. So that's the thing. I don't have time to talk about the technical details. To use a statistical approach to do this. And basically, finally, we will build this network based on the differential equation. This is like a dynamic system, and also it's a network. So this model have dual properties. It's a differential equation, which is a dynamic system, and at the same time, it's a network. So it's a dynamic network. So this is similarly, we can do, we also collect data at a protein and the molecular level. We use proteomics and also flow cytometry, antibody, proteomics, all these things. We measure the protein level response for these mice and humans. And I don't have time to talk. This model is similar to the gene. It's also high-dimensional differential equations. Then we model the protein level separately from gene level. And another one is the cellular level. Okay, I don't have time again. So for the cellular level, this is like the lung, this is the spleen, this is the lymph node, this is the blood. Blood basically link all these compartments, all these organs together. So major immune response are in the spleen and the lymph node. So that's why we focus on these two organs. We cannot do all the organs. That's too complicated. Okay? You don't have money to measure so many things. And also we measure a lot of things in the blood, and also definitely in the lung. We know that flu virus will infect our lung. So a lot of activity over there. All these immune response cells have to move traffic to the lung to kill those viruses or kill those infected cells. So each of these different type of cells is one box, is one equation for us. And so basically, when we write down all the different equations, this is the cellular level equation. Not many, 18 of them. It's actually 18 of them. It seems like not many. Like a gene level is thousands. Protein level also another hundreds of them. This is just 18 for the cellular level. You know how many different equations for the rocket? When you do that process, usually 20 to 30 different equations. You can do that accurate. And this is 20, 30 equations. I already get several thousand of them for the biology, even just several organs, not all. So this, we fit, this is the mice data fitting, model fitting. This is the 18 different equations for the cellular level model fitting. So you can see the data. The data is the data. The curve is fit the model. You can see how big the noise is. This is the lab data, very good lab. Those immunology labs are very good in Rochester, actually. Like one of the lab every year is nominated for Nobel Prize, but he never get it. But he's very good in immunology. But you can see that some of this data looks good, when you fit these different equation models, like this one, this antibody, I believe. So when we try to fit this data to our different equation models, it's not easy. Even just 18 equations with 74 parameters. These 74 unknown parameters try to fit. This takes one of the faculty and junior faculty for several months to make sure it's fit. Still it's fit, but may not be the best solution. So that's a lot of tweaking for the parameter fitting. So then the question is, after we do these models for gene level, protein level, cellular level separately, then with this like this is like a within cell in the gene level, this like protein level, this cellular, this organ level. The question is, then we need to vertically link them together into a system. So that's more challenging. Again, that will be much more than thousands of different equations. That's really, really complicated. We are trying to develop new methods, how to even use a computer to handle these thousands of equations with millions of parameters. You have to estimate those. If it's you know all those million parameters to do simulation, that's easy. The computer can do it. The question is you have to estimate those millions of parameters, and at the same time you have to compare different type of models to do model selection. So that's the challenging things when you build these thousands of different equations. We develop a separate least square approach. Try to handle high-dimensional different equations. So standard nonlinear least square method doesn't work. So we have to. I don't have time to talk about this. Basically, we show our new methods actually is much more efficient than the standard least square nonlinear least square estimation. We still need to use a supercomputer to do it, but at least we can do up to 1,000 dimensions of the different equation. This is our new method. We can still get the result. Here is the residual and also the time to use. But for the standard method, only up to 100 dimensions to 300 dimensions, there's no convergence. You cannot get the results. It's too slow. So that's the thing. We have to develop a novel methodology, algorithms to deal with this high-dimensional model construction. And also as a statistician, we always prove some theories. Otherwise, we cannot publish in the top statistical journals. I don't want to talk about that. And at the same time, besides the linear, I just show you simple linear differential equation model, very simple, even thousand dimensions, millions of parameters. But the question, we have to extend that to nonlinear models. That's why I mentioned earlier. All those elements relationship are nonlinear. None of this is linear. So that's linear is just the first step of approximation. So then we have to extend all these linear models into nonlinear models, even non-parametric model. Non-parametric model means Nonlinear model means I know the form of the function. Then I can try to estimate the parameters. Non-parametric means even I don't know what form. It's exponential, sine, cosine, or what is nonlinear, I don't know. So I have to determine the functional form first, then to estimate parameters. Then I have to consider interactions. Right now, I just consider additive. Each gene or each protein only additively have an effect on another gene or protein. But how to consider the interactions? So that's making the model more and more complicated. That's the thing. We are trying to develop all these different kind of tools, models. Finally, we want to build a library of models. Then that data go to that library to pick. If the computer is powerful enough, automatically do it. So otherwise, for the human being, even imagine if I write down the nonlinear model, 1,000 of them, how can I write down it? So you cannot do it manually. You have to let the computer do it. So that's the thing. We have to develop the technology. Basically, after 10 years, this project, center project produced about 132 papers, and that's the publications. But also we definitely develop tools and the database, not only papers, push us to develop tools and methods. And like we have the data management tool. This is the tool. I hired like about 8 or 10 people. Develop a database to manage all these different multi-level data, like gene, proteins, a lot of clinical mice, both animal and clinical. So that's this based on the so-called LabKey open source database. And also we develop software to like D-Discover. This is like a different equation model fitting. And this is how to fit nonlinear differential equation models automatically based on the data. And also DNet Weaver is a high-dimensional differential equation model fitting, like variable selection software tools. This is free. It's online, it's free. And also we develop a portal to share all these models, these tools, these software codes, and the data. So we do have a the web portal for this purpose. And also recently we are trying to restructure GEO, gene expression database, and also try to build another database, try to integrate 25 separate databases for the relationship of genes, TFs, and macroRNAs. Try to integrate all this. So these two, actually, I just start to talk to Hua and James here to collaborate on these things. Hua and I try to write a proposal, almost done on this, restructure GEO, because yeah.
What does this mean, restructure?
Restructure GEO, okay. The GEO, the gene expression database, it's hard to identify the data you want. Like, for example, I want a flu data with 10 or more time points. With all the particular flu, H1N1 flu, how to do it? You have to go to the summary or their design to use text mining, whatever the way, or keyword. You can do the keyword search, but it may not be a good way, to find. I may not find all. Usually I find 2 or 3 of them. How can you find all the data sets from GEO? Right now, GEO have more than 60,000 data sets over there, from different diseases, different experimental conditions. If I want to define a particular experimental condition for particular disease or particular situation, how can I find those data? So that's why the GEO is designed just for data repository. People dump the data over there. It's not a well-designed relational database. So you have to not redesign, but at least you have to identify, use a text mining or whatever approach to identify those metadata, then put it into a relational database so that people can easily identify the data you want. So that's the thing. And this one is just there are many databases curate a lot of like a relationship between genes, TFs, transcription factors, and also macroRNAs. But it's hard for people to use. They're spread out many places. We try to integrate all this together. And in the future, we try to also use the literature to curate more about this. This is we just published this last year, several months ago. It's quite popular now. Oh, what's wrong? And also we developed like RNA-seq data analysis, diagnosis reporting system for the doctors to use for the diagnosis. And also we try to develop a recommender system for papers, grants, conference, reagents, for people to easily integrate literature or different knowledge into the modeling, modeling work. So that's the tools, we try to develop. So this is the restructured GEO database, basically. I don't have time. So because we identify like a different cell type, if you want to look at, what kind of cell people measure the gene expression. Like the stem cell is the largest one, about 3,000, more than 3,000, close to 4,000, studies use stem cells. Like 2,000 number use T cells. 1,800 use fibroblast. So different people use different cells to measure gene expressions. All the, for diseases, cancer is the most, like 7,200 for cancer. The most of this for cancer. There are some of the other diseases. So the question how to do the text mining to identify what disease, what cells, what time points, whatever those information. That's the restructured EO. So this is the database for the relationship among genes, proteins, and also the microRNAs. So we build this network, database for people to use. So that's the thing. Okay. So summary, I'm pretty quick, and we are trying to use different equation models, even simplest mathematical models, I think, to describe a multi-scale biological system, similar to a rocket. Try to mimic the rocket way, how to do it, and also try to generate use experimental data to construct the model to estimate the model parameters. So that's the thing. And also we try to use these e-static models to understand, the interactions between our body and the pathogens and for prediction and decision making. That's the person. Definitely, this is far away from precision medicine. Okay, it's not always. You can see the data is so noisy. So it's just the, we only get $22 million. That's more again to do the really precision medicine. We just do a little bit. Just for immune system. So the future, it's very challenging future work if we really want to do precision medicine. So basically the data is too big and too many varieties. So that's problem. And the model is too complex and too many choices. I'm not sure even the simplest ordinary differential equation is the best. So I just try the simplest one because even the simplest one is so complicated. So that's the problem. And there are too many unknown parameters. Dimension is too high when you try to deal with that. You really need a big computer to do things. And possible solutions is too many. You can use different models, different parameters. You can get always similar results. The question is which one is right. So that's the thing. And also for decision making, it's too difficult actually to do this. I haven't think about this. And traditional statistical approach usually doesn't work. That's I show you. Standard method doesn't work to deal with high-dimensional big data from precision medicine. So that's why we have to develop novel approaches. And so ongoing work in the Biostatistics in the School of Public Health, in the last semester, I just joined the school and started to organize a big data working group there. And about 16 faculty plus some postdoc students, are participating in the working group. We are trying to work on different kind of, projects, and we divide people into smaller working groups. Like I'm leading a group like doing the high-dimensional time course data for event predictions based on the omics and other mobile device data. And also some people working on the imaging or video data. And also some people try to integrate the genomics, transcriptomics, and epigenetics, image and phenotype data together. And also some people work on the multi-skill model like I presented. And also some spatial temporal data like from air pollution and satellite. And the network data. And also some of the faculty work on the big data, methodology theories. Like I said, we really need to develop novel things to deal with these new things. And hopefully this semester, and from this semester or this new year, we can expand the working group to include you guys, and also maybe RISE or maybe other, institutions locally here at least. And in particular, we hope besides statistics and the mathematical modeling, we expect to incorporate more informatics approaches, computer science or domain-specific scientists knowledge, to help us to expand this, work. And so the new big data research topics include the experimental design for the precision medicine. And again, another thing is I call it knowledge power data analysis and modeling, and also the use the rocket science approach to do the multi-skill system modeling, and also personalized modeling. Personalized modeling means you have to build a different model for different person, even different subject. How can you do that? Do you have enough data to do that? Otherwise, if each person is different. You use a common model to prediction may not work. And how to deal with the incomplete data in analysis. So that's the thing. Even for the precision medicine, you invest a lot of money. You're supposed to recruit 1 million subjects. For each subject, they designed to collect so many data. I don't think you will get all the data for each subject. Nobody will spend so much time let you draw the blood or do so many things, right? So the question is how you design the study so that this group of people measure this part of variables. Another group of people measure those kind of assays, whatever the things, and so that you still can put them together to be efficient to achieve your goals. That's the design issue, and also how to deal with so-called, it's not missing data, it's incomplete data. We call it incomplete data by design. So that's the thing, new methodology we have to work on. From an educational perspective, we are trying to develop first we try to develop a concentration in data science. We have the Biostat PhD master degrees. We try to do this. Then probably in the future we have to develop a degree program for data science. That's the goal. In the long run, hopefully we can, the two schools work together to do this. And we already developed 3 courses for this concentration, and I call data science analytics methods 1. I'm teaching, start from yesterday. I start teaching this course now this semester, this first time. And we also developed a second one, the analytical methods 2, that will be taught in summer, this year. And the 3 will be a more advanced, approach, and there will be a future, I don't know when. But that's the teaching we are doing. I'm not sure I have time to talk about what we cover for these courses. Basically, this is more like data mining, machine learning approaches. For the first one, right now I'm teaching, and so like all the regression, sparse regression, this is a very standard, like outlier detection, association rule learning, whatever, those kind of tree-based approach. So the 2 is more like dimension reduction, like principal components, multidimensional scaling, all this manifold learning, nonlinear dimension reduction is a little bit more advanced, and but also includes some parallel computing technologies. So that's the thing we expect to cover. For the 3, more advanced approach for data science will include more fancy stuff like network analysis or graphic models and natural language processing. I hope you guys can help to teach these things. We don't know how to do this, the text mining or natural language processing, and data analysis for location-based services, and also real-time data analysis of predictions, and a statistical method for recommender system design, and also multi-skill, multi-level data integration, and object data analysis. So object is another new area a lot of statisticians are working on, which means that you treat one object, not one number, but a whole object as one data point. How to do the integration with that. So that's the plan. Basically for the conclusion, my understanding, precision medicine again will not work if just a huge amount of data from larger cohort randomly collect. You just put there. This doesn't work. Okay, system thinking is required. We need to understand a human body. It's a dynamic, complex system with all elements linked in a mechanistic way. We have to find a way to link them. They are not random. Even we are trying to randomly recruit 1 million people, randomly to collect something, but they are not random. Then precision medicine really require precise and personalized modeling. So that's the, that's the thing. And again, most of the work I present, today is past 10 years work, from collaboration with many colleagues, at least 10 faculty members, 15 postdocs and programmers, and maybe research associate programmers, and 20-something postdocs, many other students to work on. This is the picture from my group back in Rochester. We have 20-something people. So I have my experimental clinical collaborators. So this guy, Martin, is a co-PI, as I mentioned. David Tauber is an expert on CD8 T cells. Tim Osman is a CD4 T cell expert. He's always nominated for Nobel Prize. He's invented one of the TH1, TH2 T cells. His paper in 1980 or something is always the highly cited paper. And Dr. Livingstone is a dendritic cell expert, and Dr. Ward is a virologist, and Martinez is also a virologist. Steve Wiley is our genomics core director, and Dr. Trainer is a clinician doing the vaccine trials for flu. So that's these people actually collect all those data we used. Design. Coordinate all the experimental work. So that's all I have. Thank you.
We have time for maybe one question. We have a class.
Yeah.
the model we built based on very nice design for human body and animal models. Very beautiful, but also, as you said, $22 million is not enough. So have you thought about using some other simple model to get some, the information going back to the more higher level model, like a cell line? I know many theoretical biologists using cell line to generate data and to mimic what happens in the cell and then back to the human body.
Right, yeah, that's the, even before this, that's the work even before this for the exploration, right, to find something. That's the knowledge, I thought people have done that, that's why we try to use the knowledge, literature mining, all those existing databases, people already curated all those knowledge there. We try to use it, in the modeling. Yeah, there are a lot of people have done a lot of those, in vitro.
So in that case, because you have both ways to look
Right.
at the data,
Right.
which kind of major lesson you learned? The cell model, cell line model, is it working?
Yeah, cell line model is more clean. Yeah, cell line model is more clean. Noise is smaller, but not realistic because you didn't consider all the human body, a lot of interactions among the many things. It's not just purely cell line in the tube. So it's pro and cons. People always question us, even why you use mice model. That's why mice model matters for human. Response. Can you adapt your mice model to the human response? People always question that. For the human, I cannot kill a person to collect data from lungs. I cannot do that. The only thing I can do the mouse. Definitely, I can go back to the tube to do the in vitro experiments. But see, people always question that, how that relates to your, immune response to the human. So that's the, always, challenging question to answer, I think. Yeah.
So I'll take the last question, and I think Trevor has to start his class. You mentioned cursor dimensionality, and this does seem rather daunting. But at least in some experimental areas, probabilistic programming and hierarchical Bayesian models, they've been able to at least control that somewhat through hyperparameters, right? Because you can, a few examples, you can suddenly learn the hyperparameters that helps constrain everything else.
Right.
So do you see an analog of that here somehow in some of the techniques?
You mean
nothing conserved across levels?
You mean the Bayesian?
Well, or just that whole concept of having higher level parameters that somehow can help constrain a more massive set of parameters.
Yeah, I mean, that's what the next step we are trying to, when you try to use the knowledge or use something, you have to use the Bayesian framework to try to build hierarchical models and to learn not only from our own experimental data and also public data and also the knowledge from the literature. So that's I mentioned the 3M strategy. Yeah, that's the thing we try to move to. But the only problem when you move to the Bayesian approach, framework, the computation is a problem. We already have a computational problem. When you move to Bayesian, you have to do Markov to Monte Carlo. That's really time consuming. No, you cannot do the high dimensional. That's the problem. That's
well, I would say a lot, but defense is now funding probabilistic programming frameworks. There's a lot of work going on in that area.
Yeah.
So hopefully,
yeah,
get better.
yeah, hopefully, yeah. Yeah, thanks.